Hey math friends, it's Dakota, and today I'm coming at you with another math video. So this is for topic 5.9 of the IB curriculum in math standard level, and this is all about the normal distribution. So, normal distribution might sound pretty familiar. Distribution is something that's talked about since elementary school math, but you may not remember it called that. As we know with data, sometimes our data can be skewed going to the left, skewed going to the right, or it can be all over the place and have no pattern. But sometimes in math, there's this really cool phenomenon that happens where our data gets perfectly, well, almost perfectly symmetrical. And this is called normal distribution because it's normal. So, symmetry, as you may remember from geometry, means that the data can be cut down in the middle and it'll have equal distribution, not necessarily values, on both sides. And it also may look like a familiar shape. This is called the bell curve. You may have heard teachers before grade their students' tests or projects using something called the bell curve. So, tests is something that can be measured by normal distribution. This means that the grade boundaries for each person's final grade is determined by how well or how bad everyone did in the class, meaning that the standard deviation got pulled one way or got pulled another. Another way we can model normal distribution is by height. Let's say the last time you went to the doctor, they told you you were in the 70th percentile for kids your age in height. That would mean that if you took a group of kids who were your exact age and you took 70% of them, you would be taller than that 70%. Or, likewise, if you lined everyone up in a line all the way, if you had 100 students, you would be the 71st person. So, let's talk about some other parts of distribution. You may remember from prior learning that the most important parts of looking at distribution and probability and data in general is the mean, median, and mode. You also would have used range a lot, but instead of range at this level of math, we prefer to use variance. So, mean is the average of your numbers. That means when you take all of your numbers and you add them up and you divide by however many numbers you had, then that is your mean, meaning on average, that's the number that will happen. Median is your middle data set, well, your middle data point. So when you line all your numbers up, like 1, 2, 3, 4, 5, 3 is your median because it's in the middle. Or for mode, that's the one that occurs the most. So in a number lineup, 2 would be your mode because it appears the most. But what about variance? And where did range go? So you may remember from any prior learning math class you've had that range is simply the highest subtracting the lowest. Now this is a very general way to look at the variance of a distributed statistic set. So this is very similar to the concept of range. Variance in a data set is going to very specifically seeing, just like in the name, how much the data varies. There also is something called the standard deviation. So, the standard deviation, when you get into higher math, is simply the square root of the variance. Pretty cool, huh? So, in math, we really like to use this cool guy right here because it can tell us a lot about the data. So, there are some other special things that we should know about normal distribution before we continue on. So, do you know what's really cool about this? Is that standard deviation tells us how far the data is spread out from one another. so that way we can know more specifically. What's cool about that is that, again, if you have a handy dandy little bell graph, and you were to imagine that here's the mean, and here's a data set, a chunk, and here's another chunk, and here's another chunk, and here's another chunk, we are able to classify these chunks by themselves. One chunk of this is called the standard deviation. Later on, we're going to be calling this the z-score. The z-score is simply an easier way to give a unit value to your standard deviation. Instead of saying standard deviations or saying the standard away from, we're just going to use z-score. So, but something really cool when we're thinking about standard deviations at a basic level is that 68% of the values are in one standard deviation. What's even cooler is that 2 deviations is 95. And after that, 99.7 of that data is right there. We can never be fully sure when we're predicting statistics, but we can get pretty darn close. So, here are some takeaways we can take away from that. One deviation, so if you have one full standard deviation, you can call that being as likely. As you get further on, the chances that your event will happen become more and more likely. But what about if we need to determine things more specifically, instead of just saying, oh, well, this shaded in region or this shaded in region? How can we get more specific when we're talking about bigger things? Like, let's say the size of fish in a market or the amount of coffee beans inside of a coffee pot. Well, there are some really cool ways to do that too. So let's come back to our z-score here. Something really cool in the IB curriculum is our formula booklet. So if we take a look at our formula booklet, we see something really cool about the z-score. We find a formula that the z-score simply equals the x value minus the mean, all set over your standard deviation. So, where can we get that from? Well, something that you may sometimes see in an IB exam is something that looks like this. So what this means is the probability of this event, and these two values here are the mean and the variance. So like I said before, the variance is just the standard deviation, but squared. So we will be able to come back and use this later on. So this is really fun because now we can determine how many standard deviations there are, and more specific. We don't have to just find simple z-scores. If we wanted to, we could say, if it's given to us that x equals 5 and the mean equals 2 and the standard deviation equals 2, well, we could simply say then that the z-score equals 5 minus 2 over 2. Or, in better terms, the z-score equals 3 over 2. But what if I don't want this to equal? What if I don't know what it's going to equal? What if I just want a probability of something? And what if I want to have a z-score that's greater than or less than or equal than? Then what do we do? Well, let's try some of those out. So before we get to the super cool high-level IB problem, and before we start to think about using this in a probability sense, let's just talk about figuring out the z-score again. So suppose that when given that the mean of a set of data is 926, and that the variance of a set of data is 4, how many standard deviations is this away from the mean? Now, this may be a lot of words, but we can break this down. So like we said before, this is telling us that our mean equals 926. And something really cool is that this sign means mu in Greek. So you can remember that as mean, the little cat. He's saying, you can do math. I'm gonna give you a little thumbs up. So let's continue on with mu, the mean cat. So we have 926 is the mean. What else do we know? We know that 4 is the variance. So because we don't want to work with the standard deviation squared, which is 4, we can just square root it. So that means that our standard deviation for this problem is 2. Oh, that's really cool. So now we can plug this back into our super cool formula from our formula booklet and figure out how many standard deviations is this from the mean. So remember that when they want us to find a certain amount of standard deviations, they want us to find the z-score. So let's say that z equals our mean, z equals our x minus our mean over our standard deviations. Well, we might not necessarily know all parts about this yet, so that is okay. It may seem a little tricky, but I promise you it'll get better. So we need to pick out a value for this. Let's choose x is going to equal 102. Cool, now we can plug this back in. So our z-score equals 102 minus our mean over our standard deviation, so 2. So our z-score, well, before we get ahead of ourselves here a little, let's make this a bigger number. Let's say it's 1020. So we need to take out our fun TI-84 Plus and figure this out. So 1020 minus 926 divided by 2 equals 47. So the z-score for this equals 47. But what's another way to think of z-score? Z-score can also be thought as the area. And once we get into the percent, we are able to find the percentage of this area to find out what our data looks like in terms of probability. So, looking back at this problem again, let's say we needed something more broad. Let's say x does not equal 1020 and actually is greater than or equal to 1020. Well, this is where we can use some other really cool techniques. So once you get here on your calculator, you're going to want to put your z-score that you found where on here it says upper. So you're going to go ahead and, wait, actually you're not going to put your z-score there. I'm sorry, I got too excited and misspoke. Actually, the best way to do it is to put in the, oh my god, hold on. Okay, winter's not showing up. Okay, moving on, we're going to move on to using probability with this. So, in this question, we're given that our mean is 10 meters, our standard deviation is 0.5 meters, and they want us to find the chance that it's between 9.2 and 11. So, let's break it down again. we know here that our mean equals 10, our standard deviation equals 0.5, and we want to find the chance it's between a number and a number. Well, what would this look like? So, let's assign it a fun variable. How about x? So, we're going to use x here. We're going to say that 9.2 x and 11. And then we're going to put the cool little guys there. So, if it's between these numbers, it also means that it can equal those numbers. Now, we want to put this here and put our probability sign. This might start to look pretty familiar to some stuff you might have learned in 5.7 or 5.8. And that's a really good thing to be able to recognize here because it's going to help us a lot. So, once we know this, we can figure out this more specific. The best way to figure out problems like these is to be able to break them down into two parts. Looking specifically at 9.2 is less than or equal to x, and x is greater than or equal to 11. So the way that we can look at this is something that is really cool. So when we go back here, we can find that we can make a new equation. So the kind of equation that we're going to be making here is using something that is a k value. So the k value equals the quantile, or the percent that there are less than or equal to. So k is going to be super important. So I'm going to put super important. Now let's continue on with this. So coming back over here, we can use a brand new equation. We can use something that equals k. So for this equation, now we're going to use that k, which remember is the probability of something happening, is. So another really cool way that k can be written here is also as the probability that z is greater than z, or vice versa. You can change this to whatever allows for it. So basically what this is the inverse of z. So when we look at these here, this is still our given x value. But now what we want to do is find our z-score and subtract it from 1 to find k. So now we're going to do 1 minus 9.2 minus the mean over 0.5. Now this is a really important step to do here because you cannot have a negative z-score. Now, looking over here, we can do the same thing. 1 minus, but because this one is already greater than 10, we don't have to worry about this one. This one is more of like a regular one. So here, we're going to do the 11 minus 10 over 0.5. So now, once we find both of those values, we simply just add them together, and that will give us our answer. So in order for time, we're going to move on from there, but that's how you would find that. So now we're going to move on to a more exam style question. So this question here says, the weight in grams of beans in a tin is normally distributed with mean k and standard deviation, or a mean of mu, it looks like a k, and a standard deviation of 7.8. Given that 10% of tins contain less than 200 grams, find, and then they ask us a lot of things. So I already got us started here on part A. So we can remember the really cool formula from our formula booklet, which is really the only new equation you're going to learn in this specific subtopic of the topic at the standard level. So we don't know the mean yet. That's why I blocked it out here. So this is blank for right now. But we do know some things. So what we do know is that the probability that x is going to be less than 200 does equal 0.1. That's what it said here. So now that we know this, we can use our TI-84 plus. So as you can see here, when you go to second and then go to vars, you go down to 3 where it says inverse norm. Going to put in our area. Okay, so 0.1, press paste, and there is our equation. So we're going to use that number to help us figure the rest of this out. So now what we really can do is make a brand new setup. So down here, we're going to write that negative 1.28 is actually going to be our really cool new spot where we are going to be able to input this information and say that it's equal to 200, because that's our x now, because we did the inverse, is equal to 200 minus our mean, which we're looking for, over our standard deviation, which we found out was 7.8. So now you can solve this like a normal math equation. Now when you do all the bells and whistles and you figure this out, you will see that the mean of this equals, really cool like, it will equal 209.996, and it'll keep going on and on. So that's why we can say this can just be written as 210. So let's move on to our next part, part B. Now part B asks us to find the percent containing more than 225 grams. So they want us to find the probability that some random variable represented by x is going to contain more than 225. Well, now that we know our mean, we can plug it back in. And this one will be much faster now because we don't have to think around all these new concepts that we just learned. So now we can say that if our z-score equals x minus mu over theta, that our z-score will equal our x. So our x value given to us was 225. And remember, because we are going to be using it in the context of it being greater or less than, that we want to be able to use it like this. We are going to say the x value is going to be represented once again by that really cool nifty z-score that we found before. So remember when we were doing this before and we found out that when you have a z-score, you were able to find this. So our z-score, when you're not considering it to be inversed, like we found up here, actually turns out to be just 225 minus 210 over 7.8. So this is where we find out our z-score is actually somewhere around 0.973. It's an estimate. So now that you have this number, you can plug it back in over here. So we can say that for this, which we can write k again, if that makes more sense for you as we're going through this, that since this is our z-score, we can just do 1 minus this value. Because if we know what the z-score is when we have 225, instead of having to individually find all the values greater than it, we can just do 1, which, as you may remember from last topics, that when you have all the probabilities, they will add up to 1 when you add them all together in a line. So we can do 1 minus this value. That's really cool. So 1 minus 0.973 equals 0.0274, or somewhere around there. But we want to put this now into percents, because remember that when we're working with probability, we want to use percent, which is area, and not the z-score. We want to use this fun k value. So what we're really going to say is that the probability that that random variable x is going to be greater than 225 grams is actually going to be equal to around 2.7%. So now we can move on to our last part of this. So I'm going to go ahead and come back. Hey guys, so I went ahead and I transferred over the important information from the problem onto a new page so we can do some more working on it. So, what was given to us in part C is that when we have a random variable x and we have a normal distribution, the mean is now 205. And we don't know what the standard deviation is, because there's a mix-up at the bean factory, and they had to do a new computer program, and they found that they lost some beans in the process, and they gained a few somewhere else. And so now, these are our new values to work with. But you can use some of our old things for what they're asking us specifically. So for here, they're telling us something with the probability again. This time they told us 98% of tin cans that are between 200, so we're going to say greater than 200. Let's see, T for tin can, and are that are between 200 and 210, you want us to use this to find the value of theta. Well, this can be a really simple way. So, remember how we were able to find out before what 10% of our data was. So this 10% was all the data that was less than less than 200. So something that we can take away from this is that we're going to be using this same process again. We want to find it the inverse way one more time. But remember when we drew our bell curve before? And I told you guys that in your little bell curve, that all of this accounts for about 99.7% of the data. Well, we know 98%. So we know this area already. And Barry told us that 98% of this data was from here to here. So what we want to set all of this equal to is actually this 0.1% that's left here. So this time in the calculator, go to second bars. I'm going to go to our inverse norm and put in our 0.01. I'm going to paste. So this is going to be our new inverse value. So now we can say that when we inversed it, which remember we used as a k value before, is also sometimes written as this. This is going to equal negative 2.3 3, rounding to 3 sig figs. And this is really cool information to use now, because now the rest of this problem can be really simple. So now what we're going to do is we're going to show how 210 minus 205, because remember the new mean that was given was 205, and the x value that we're going to be using is 210. It's just the one that I picked from here, just to be easier, over our unknown standard deviation. It's going to be equal to our negative 2.33. So what was really cool about this is it looks just like a regular algebra equation. So I'm going to multiply our theta on both sides, and going to do this up here. So this turns into 5 equals negative 2.33 theta, and divide by this negative 2.33 on both sides, and it finds out that our theta actually is about, let's do it all together. Oops. Negative 2.15. So that's our final thing for finding the last part of that one problem. So I hope this gave you an introductory learning to topic 5.9. Remember that this was 5.9, and this is called the normal distribution. And till next time, me and good old me and the cat hope that you have enjoyed this video and that it has helped you a little bit. And until then, me and the cat would just like to say mew. Thank you.